Tonight we explore how Jupiter quietly shapes the solar system, regulating comets, stabilizing planetary orbits, influencing Earth's climate cycles, and even helping create the conditions that allowed life to persist. We'll uncover how its immense gravity redirects dangerous objects, organizes the asteroid belt, affects Earth over deep time, and why scientists consider it a regulator rather than a simple shield. Everything that follows is already happening, slowly, invisibly, and continuously. We begin with Jupiter's size and the gravitational dominance that allows it to shape everything around it. Jupiter is the largest planet in our solar system, carrying a mass 318 times greater than Earth's. Hold that number for a moment and let it settle into you the way deep water settles after a stone has passed through. 318 Earths, not in volume, but in mass, in the sheer gravitational authority of the thing. All the weight of continents, all the oceans and iron cores and spinning molten hearts of every rocky world in our neighborhood. And still Jupiter outweighs them all, combined by a margin that feels almost like myth. It sits at the center of its own gravitational story, and everything else, comets, asteroids, even the slow drift of distant moons, moves in response to it, the way a breath changes when someone enters a quiet room. Jupiter's gravity influences the orbits of nearly every object in the solar system. This is not a local force, not a neighborhood phenomenon. It is a reach that extends across hundreds of millions of miles, threading through space the way a melody threads through silence, touching things it never touches directly. The asteroid belt stirs in response to it. The farthest comets feel its pull on the long, slow arc of their return. Even the planets themselves, in their deep geological time, have shifted fractionally in answer to Jupiter's patient tug. Gravity at this scale does not announce itself. It simply is, a constant, invisible hand resting on the scale of the solar system, keeping the balance that billions of years of life have quietly depended upon. Jupiter's gravitational field extends tens of millions of miles into space. To understand this is to understand something about the nature of influence, how a thing can be felt far beyond the place where it lives. Jupiter's gravity does not stop at its clouds, does not end at its moons. It reaches outward like the low hum of a great instrument, vibrating through the fabric of the solar system in every direction, touching the path of every wandering rock and frozen comet that drifts across its range. Scientists measure this influence in the subtle bending of trajectories, in the way small bodies slow and curve when they come near. It is a whisper that carries for a very long way, and in the language of orbital mechanics, that whisper has shaped the solar system we call home. Jupiter's mass is greater than all other planets in the solar system combined. Say that slowly. Every planet, Saturn with its magnificent rings, Uranus tilted dreaming on its axis, Neptune storm-wrapped at the edge of the known, all of them together, pooled into one imagined world, still would not outweigh Jupiter. It is the dominant note in the solar system's chord, the one voice that all others must tune themselves around. This is not about beauty or brightness. Jupiter is not the most beautiful planet, nor the most dramatic to human eyes. But in the grammar of gravity, in the physics of how worlds persist and orbits hold, Jupiter is the sentence that all other sentences must answer to. It is the great given, the immovable fact around which everything else revolves, quietly, patiently, for billions of years. Jupiter's gravity bends the paths of incoming comets, often flinging them out of the solar system entirely. A comet born in the distant dark, assembled over millions of years from ice and rock and ancient carbon, begins its long fall inward toward the Sun. But if its path carries it near Jupiter, something changes. The planet's gravity reaches out like a river current, invisible and irresistible, and the comet is redirected. Sometimes it is bent into a new orbit. Sometimes it is flung outward at such tremendous speed that it escapes the solar system entirely, sailing off into interstellar space to travel for an eternity in silence. Jupiter is always doing this, always mid-reach, mid-redirect, a quiet force operating at distances we can barely imagine, adjusting the trajectories of objects that will never know they were touched. Jupiter's immense gravitational well creates a powerful clearing effect in the outer solar system. Gravity, as Einstein understood it, is not a force that blocks like a wall. It is a curvature in the fabric of space itself, a deep well that objects fall into, spiral around, or are redirected by depending on their speed and angle of approach. Jupiter's well is the deepest in the solar system after the Sun's. Objects that wander too close are either captured, as some of Jupiter's irregular moons once were, or flung away at tremendous speed. This clearing effect, this tendency of Jupiter's gravity to reorganize whatever comes near it, has over billions of years created a solar system with far less random debris wandering freely through the inner regions where Earth quietly turns. The well does not block the universe, it simply reshapes it. Jupiter is 1,300 times the volume of Earth, making its gravitational reach almost incomprehensible in scale. Volume is different from mass. It is the space a thing occupies, the room it fills. And Jupiter fills a room that staggers the imagination. If Earth were a grape, Jupiter would be a basketball. If you lined up every human being who has ever lived one after another, shoulder to shoulder, the line would not come close to spanning Jupiter's diameter. And yet all of that size, all of that volume is gas and storm and compressed hydrogen. A world with no solid surface, no ground to stand on, only depth upon depth of atmosphere descending into pressures that crush steel. This immensity is what generates the gravitational reach. The bigger the mass, the deeper the well, and Jupiter's well has been pulling the solar system into order for longer than the first life appeared on Earth. Jupiter acts as the solar system's dominant gravitational force after the Sun. The Sun holds everything in orbit. That is understood, that is the center of the story. But Jupiter is the second voice in that duet, the harmony beneath the melody. When scientists model the long-term behavior of the solar system, how orbits evolve over millions and billions of years, Jupiter is always the dominant variable. It tilts the asteroid belt. It shapes the trajectories of comets. It locks smaller planets into predictable patterns through orbital resonance. Without the Sun, there would be no solar system. But without Jupiter, the solar system the Sun governs would be a different place. More chaotic, more randomly violent, less like the quiet, ordered neighborhood in which life had the patience and the peace to emerge. Jupiter's gravity can accelerate comets to such tremendous speeds that they achieve escape velocity and leave the solar system entirely. Escape velocity, the speed a thing must reach to break free of a gravitational field forever. For the solar system, that number is enormous, roughly 42 kilometers per second at Earth's distance from the Sun. Jupiter's close gravitational encounters can fling comets to speeds that exceed this threshold, launching them into interstellar space on trajectories they will follow for millions of years. This is one of the ways the solar system cleans itself, not through collision, not through destruction, but through the elegant violence of deflection. A comet that might have orbited the inner solar system for millennia, crossing Earth's path again and again, instead vanishes outward into the dark, redirected by Jupiter into a journey that has no end and no return. Jupiter's gravitational influence has slightly affected Earth's own orbital path over vast stretches of geological time. This is the subtlety that is easy to miss, that Jupiter's reach is not only felt by comets and asteroids, not only by the distant wanderers of the outer solar system, but by Earth itself. Over millions of years, Jupiter's gravity has nudged our orbit in minute ways, contributing to the Milankovitch cycles, slow, rhythmic variations in Earth's orbital shape and axial tilt that drive ice ages and warming periods across geological time. These are the deep rhythms of our climate, the long breath of the planet, and Jupiter is part of what conducts them. It is strange and beautiful to think that the ice sheets that once covered entire continents were moved, in part, by the gravitational breath of a world more than 400 million miles away. Jupiter's gravitational influence helped shape the asteroid belt into the relatively stable ring it occupies today. The asteroid belt, that vast collection of rocky bodies orbiting between Mars and Jupiter, was not always as stable as it is now. In the early solar system, it was a more turbulent place, dense with material that had not yet found its equilibrium. Jupiter's gravity stirred that material relentlessly, preventing it from clumping into a planet, and over millions of years, much of the belt's original mass was ejected, flung toward the inner solar system, absorbed by growing planets or expelled entirely. What remains is a belt depleted of most of its original material, arranged into a pattern that Jupiter's orbital resonances keep largely in order. It is, in its way, a garden that Jupiter has been tending for billions of years, rough and incomplete, but held in a shape that poses far less danger than its early form. Without Jupiter's mass anchoring the outer solar system, the orbital architecture we depend on could become unstable over time. Computer models of solar systems without a gas giant in Jupiter's position show something troubling. The inner planets, Mercury, Venus, Earth, Mars, develop erratic, shifting orbits over millions of years. Without the stabilizing resonance that Jupiter provides, Earth's orbit could become more elliptical, carrying us closer to or farther from the Sun in cycles that would devastate the climate. The stability we have, the nearly circular orbit, the consistent seasons, the reliable distance from the Sun that allows liquid water to exist, is not guaranteed by physics alone. It is in part a gift of geometry, and Jupiter is a large part of why that geometry has held, patiently and silently, across all the years life has needed it to. Jupiter has been directly observed capturing or deflecting comets headed toward the inner solar system. This is not theory or simulation. It is something we have watched with our telescopes in real time in the span of a single human lifetime. A comet falls inward from the deep outer dark, follows its long arc toward the Sun, and encounters Jupiter. What happens next depends on the angle, the speed, the precise geometry of the encounter, but the outcome is always Jupiter's gravity reshaping the trajectory. Sometimes the comet is captured, drawn into orbit around the planet, becoming one of Jupiter's temporary gravitational prisoners. Sometimes it is redirected into a new path, its original trajectory erased and replaced. And sometimes it is simply destroyed, pulled apart by tidal forces and swept into the planet's vast atmosphere, absorbed and silenced. We have seen all of these outcomes. Jupiter does not hide what it does. In 1994, comet Shoemaker-Levy 9 was captured by Jupiter's gravity, pulled apart into more than 20 fragments, and then drove each fragment into the planet over 6 dramatic days. It was the first collision between two solar system objects ever directly observed by humanity. Astronomers around the world and the Hubble Space Telescope in orbit watched as fragment after fragment, each piece of a comet that had once been whole, plunged into Jupiter's atmosphere at 60 kilometers per second. The impacts created dark scars in Jupiter's cloud bands, some of them larger than the entire Earth. For 6 days, the solar system showed us something ancient and primal, the raw physics of collision, the violence that underlies the apparent peace of the night sky. And Jupiter took every impact as it has taken countless others, quietly and completely. The Shoemaker-Levy 9 impacts released energy estimated to be equivalent to roughly 300 million nuclear bombs, energy that Jupiter absorbed into its vast atmosphere rather than allowing it to reach the inner solar system. 300 million. There is no good way to feel the weight of that number. It simply exceeds the scale at which human imagination is comfortable. But Jupiter felt it. In whatever way a gas giant feels anything, and its atmosphere churned and darkened and eventually healed, as it always does, with the patience of something that has absorbed far greater things over far longer periods. The energy dissipated, the scars faded. Jupiter continued its orbit, unchanged in any meaningful way, having consumed something that would have reshaped life on Earth had it arrived here instead. It is not protection in any conscious sense, but the outcome is the same. Jupiter absorbs a significant quantity of asteroid and comet material every year, small impactors, fragments, and dust-level debris that encounter the planet and are pulled into its atmosphere. Earth, for comparison, gains roughly 40,000 tons of cosmic dust and micrometeorites annually, most of it microscopic, most of it harmless. Jupiter's intake is larger still, though much of it similarly fine-grained. What matters is not the precise weight of material, but the pattern. Jupiter sits at the outer boundary of the inner solar system, its gravitational field sweeping through space like the slow turning of a great current, drawing in what wanders too close. The planet is, in the language of astrophysics, a dynamic sink, a place where material accumulates that might otherwise have continued inward, not a wall, not a net, but a deep place that things fall into and do not easily leave. Astronomers have observed multiple bright impact flashes on Jupiter in recent decades, each one a moment of cosmic collision made visible across hundreds of millions of miles of space. Amateur astronomers watching Jupiter through backyard telescopes have been among the first to record these events. brief flickers of light against the planet's cloud bands that last only seconds before fading. What they are watching is a meteor or small asteroid striking Jupiter's upper atmosphere at tremendous speed, releasing energy as heat and light in an instant. The event is over before most people could finish a sentence, but in that instant, a small piece of the solar system's wandering debris has been consumed. Each flash is, in its quiet way, a piece of evidence, a confirmation that Jupiter is actively, continuously engaged with the material that moves through its domain. A 2009 impact on Jupiter left a dark atmospheric scar roughly the size of the Pacific Ocean, visible through amateur telescopes for days before it gradually faded back into the planet's weather systems. The object that caused it, an asteroid or comet nucleus estimated to be several hundred meters across, struck with no warning and left a mark that, on Earth, would have covered the largest ocean on the planet. It was discovered not by a space agency, not by a professional observatory, but by an amateur astronomer in Australia who noticed something unexpected in the familiar cloud patterns he watched every clear night. Jupiter received the impact. Jupiter's atmosphere processed it. And within days, the great bands of cloud that circle the planet had begun, slowly, to erase the evidence, the way a deep lake eventually stills after a stone has fallen into it. Jupiter's position at the outer boundary of the inner solar system makes it a natural interceptor of objects approaching from the outer reaches. The solar system's geometry matters enormously when thinking about impact risk. Objects that originate in the outer solar system, long-period comets from the distant Oort cloud, for example, must travel a vast distance to reach Earth, and Jupiter lies directly in the path of many of those trajectories. Its gravitational field does not simply block these objects, it interacts with them, bending their paths, sometimes capturing them, sometimes redirecting them into entirely different orbits. Some of those redirected objects do end up on trajectories that cross Earth's path. Jupiter is not a perfect filter, but many others are deflected away, their encounters with Jupiter replacing what would have been a continued inward journey with something entirely different, a new orbit, an outward fling, or a final collision with the planet itself. Long-period comets, those with orbital periods of 200 years or more originating in the distant Oort cloud, are frequently redirected by Jupiter's gravity when they enter the inner solar system. These are among the most dramatic objects in the solar system. Enormous frozen bodies, sometimes miles across, falling inward from distances almost beyond comprehension, following gravitational paths set in the early history of the solar system. When they encounter Jupiter, the encounter is rarely gentle. The planet's gravity grabs at them, bends their trajectories, and often breaks their original orbital patterns entirely. Some are captured into much shorter orbits, becoming what astronomers call Jupiter family comets. Others are ejected. A few are torn apart. In every case, Jupiter has changed the story, has taken a comet on a certain trajectory and rewritten what happens next in ways that ripple across millions of years of solar system history. Jupiter's role in regulating Earth's impact environment is scientifically nuanced. It is not a simple shield. Planetary scientists have long debated exactly what Jupiter's net effect on Earth's impact rate truly is. Some simulations suggest that while Jupiter deflects many comets away from the inner solar system, it also acts as a gravitational slingshot, pulling some objects from the outer reaches inward that would otherwise have remained there harmlessly. The current scientific consensus leans toward describing Jupiter as a regulator rather than a protector, a force that sculpts the distribution and frequency of potential impactors, redirecting some away while inadvertently delivering others. The impact environment Earth exists within today is in part a product of Jupiter's long gravitational influence. Whether that environment is better or worse than what would exist without Jupiter depends on the model and the timescale, and honest science holds that question open. Short-period comets, those with orbital periods of less than 200 years that make regular passes through the inner solar system, are largely shaped in their behavior by Jupiter's gravitational influence. Many of these comets were originally long-period visitors from the distant Oort cloud that were captured or redirected by Jupiter into shorter, more predictable orbits. Halley's Comet, perhaps the most famous of all comets, visits the inner solar system roughly every 75 years, an orbit that may have been sculpted by interactions with the giant planets over millions of years. In this way, Jupiter does not merely respond to comets that come near it. It actively shapes the population of comets that orbit the inner solar system on recurring schedules, setting the pattern of their paths with a gravitational authority that persists across geological time. Jupiter's gravity curves the paths of objects approaching from deep space, reshaping their trajectories through the pure physics of gravitational interaction. Gravity bends the path of anything that moves through its field. This is one of the foundational truths of how the universe works. Near a mass as large as Jupiter, the curvature is significant. An object approaching on one trajectory can emerge on a drastically different one, its speed and direction both altered by the encounter. This is the same principle that NASA uses intentionally in spacecraft missions, the gravity assist or slingshot maneuver, where a probe is deliberately flown past a planet to gain speed. Jupiter has been performing this operation on comets and asteroids without intention for billions of years, curving the paths of whatever wanders close, redistributing them through the solar system in patterns that are still being mapped and understood. Without Jupiter in its current position, Earth's experience of large impacts would likely be different, though scientists debate in which direction that difference would fall. Some models suggest that a solar system without Jupiter would expose Earth to a higher rate of certain types of impactors that Jupiter currently diverts. Others suggest that without Jupiter's slingshot effect, some outer solar system objects would simply remain in the outer solar system, never disturbed onto Earth-crossing paths in the first place. The honest picture is one of complexity. Jupiter both removes threats and occasionally creates them. What is clear is that the impact environment Earth has experienced over its history, the specific pattern of large and small collisions across billions of years, has been shaped in meaningful ways by Jupiter's presence. Remove Jupiter, and the story of impacts on Earth is a different story. Exactly how different, and whether it would be better or worse, remains an open and fascinating question. Jupiter has been described by some planetary scientists as a cosmic vacuum cleaner, a phrase that captures, if imperfectly, the planet's tendency to accumulate material from the surrounding solar system. The analogy is imperfect because Jupiter does not only pull things in, it also flings things away, redirecting as well as absorbing. But the image is evocative for a reason. Jupiter's gravitational field does draw material from the surrounding space over time, and the planet's atmosphere has consumed countless impactors across the history of the solar system. Every comet that plunges into its clouds, every asteroid that crosses too close and is captured, every fragment from a shattered object drawn in by tidal forces, all of it disappears into Jupiter's endless depth. The planet is vast enough to absorb these events without meaningful alteration to itself, and that capacity, that sheer absorptive size, is part of what makes its role in the solar system so significant. Many objects that might otherwise wander dangerously through the inner solar system are instead locked in Jupiter's Trojan asteroid clusters, two stable groupings of asteroids that share Jupiter's orbit around the Sun, held there by the balance of gravitational forces, harmless and unchanging for billions of years. These are the Lagrange points, regions of gravitational equilibrium where an object can remain in a stable position relative to both Jupiter and the Sun indefinitely. The Trojans represent material that could, under different orbital circumstances, have become a source of inner solar system impactors. Instead, Jupiter's gravity has sorted them into a kind of permanent parking arrangement, two great clouds of rock and ice preceding and following the planet as it circles the Sun, companions in orbit, neutralized by the same gravitational logic that Jupiter imposes on everything within its reach. Jupiter hosts over 12,000 known Trojan asteroids, rocky bodies locked at two gravitational equilibrium points in Jupiter's orbit, known as Lagrange points, where the combined gravity of the Sun and Jupiter keeps them in stable positions indefinitely. These are not random wanderers that happened to park themselves nearby. They are objects that have been gravitationally sorted and held in place over billions of years, arranged by the elegant mathematics of orbital mechanics into two enormous clouds, one leading Jupiter in its orbit, one trailing behind. They share the planet's path around the Sun without approaching it, without escaping, without drifting into the inner solar system. They are, in their way, a monument to Jupiter's gravitational authority, material that the planet has organized, named by its gravity, kept in its company across all the long years of solar system history. The Trojan asteroids share Jupiter's orbit but remain stable within it, never drifting inward toward Earth or the other rocky inner planets. This stability is one of the quieter miracles of orbital mechanics. Objects held at Lagrange points are not merely paused there, they are in a dynamic equilibrium, gently corrected by gravitational forces whenever they drift slightly. They oscillate around these points in slow, looping paths called librations, like a pendulum that never quite comes to rest but never escapes either. The result is a population of thousands of asteroids that travel the solar system on orbits parallel to Jupiter's, companions to the planet on its 12-year circuit of the Sun, neither falling inward toward the terrestrial planets nor drifting outward into the deep dark. They are held carefully by the same physics that holds everything in Jupiter's domain, and in being held, they pose no threat to the world where we sleep. Jupiter's orbital resonance with Saturn helps regulate the long-term stability of the entire solar system. Orbital resonance occurs when two orbiting bodies exert a regular periodic gravitational influence on each other because their orbital periods are related by a simple ratio. Jupiter and Saturn do not currently occupy a perfect resonance, but their gravitational relationship is deep and consequential. They are the two largest planets in the solar system, and the rhythm of their interaction over millions and billions of years has shaped the architecture of everything around them. Computer models of the solar system's long-term evolution consistently show that the Jupiter-Saturn pairing is a stabilizing influence on the inner planets. Their gravitational conversation, ongoing across billions of years, has helped keep the orbits of Earth and its neighbors in the relatively circular, predictable paths that make seasons and climates and, eventually, life possible. Orbital resonance means that the gravitational rhythms of Jupiter and Saturn synchronize periodically, and those synchronized pulses help prevent chaotic long-term drift in the orbits of the inner solar system. Think of it as two musicians playing in a room. Even if their rhythms are not in perfect time, the overlap of their beats creates interference patterns, moments of convergence and divergence that ripple through the air of the room. In the solar system, that room is space and the ripples are gravitational. The periodic alignment of Jupiter's and Saturn's gravitational tugs creates a background rhythm that the inner planets have evolved within, their orbits shaped around these regular pulses the way rivers are shaped around the rocks they encounter. The stability we experience, the mild, predictable climate, the stable distance from the Sun, is in part a product of this slow, ongoing gravitational music. Jupiter's orbital resonance with the asteroid belt creates what are called Kirkwood gaps, specific distances from the Sun where very few asteroids exist because Jupiter's gravity has cleared them out over millions of years. These gaps are named after Daniel Kirkwood, the 19th century astronomer who first noticed them in 1866. They appear in the asteroid belt at distances where an asteroid's orbital period would be a simple fraction of Jupiter's, a 3-to-1 ratio, or a 2-to-1 ratio, or a 5-to-2 ratio. Objects that wander into these resonant positions find their orbits gradually pumped by Jupiter's periodic gravitational kicks until the orbits become wildly elliptical, until the objects are sent careening into the inner solar system or ejected entirely. The gaps that remain are evidence of this process, regions of space that Jupiter has systematically cleared year by year, orbit by orbit, across hundreds of millions of years. The Kirkwood gaps act as natural clearings in the asteroid belt, regions where objects cannot maintain stable orbits due to Jupiter's resonant gravitational influence, reducing the density of asteroid populations in those zones. This matters for Earth because asteroids that enter these resonant zones do not stay there. The resonance gradually destabilizes their orbits, but the destination of those destabilized objects is not always inward toward Earth. Many are swept into orbits that remove them from the inner solar system entirely. The gaps themselves, the cleared regions, represent material that once orbited there and was redirected. What remains in the belt is arranged around these gaps, shaped by them, its distribution a direct artifact of Jupiter's gravitational reach. The asteroid belt as we know it, the specific arrangement, the specific population, is a sculpture that Jupiter has been working on for the entire history of the solar system. Jupiter's resonance effects have swept many asteroids into safer or more distant orbits over millions of years, gradually reshaping the population of objects in the inner solar system. This is one of the slowest and most patient processes in nature, the rearrangement of a solar system's debris field through the consistent application of gravitational rhythm across geological time. An asteroid might spend millions of years slowly drifting toward a resonant zone, then find its orbit destabilized over the course of another million years, then be flung outward or redirected inward over yet another long span. The process is not dramatic on any human timescale, but on the timescale of planets, of deep geological time, it is transformative. Jupiter has been rearranging the furniture of the solar system since before the continents of Earth existed, and the arrangement we live within today is the result of that immeasurably patient work. The 3-to-1 orbital resonance between Jupiter and asteroid belt objects is particularly powerful at destabilizing and clearing asteroids from that specific region of the belt. At the 3-to-1 resonance location, an asteroid orbits the Sun exactly 3 times for every single orbit that Jupiter completes. This means that every 3 years the asteroid finds itself in exactly the same position relative to Jupiter, and every 3 years Jupiter's gravity delivers a gravitational nudge in exactly the same direction. These nudges accumulate. Over thousands of orbits, the asteroid's path grows more and more stretched, more and more elliptical, until the orbit crosses the paths of the inner planets. The asteroid must then either collide with one of them or be further redirected by their gravity. This is the mechanism behind one of the primary sources of near-Earth asteroids, objects that Jupiter's resonance pumped out of the belt and into the neighborhood of the terrestrial planets. Without orbital resonance from Jupiter, the asteroid belt could have produced a different and potentially more disruptive distribution of Earth-crossing objects over time. The belt we have today is depleted, emptied of most of its original mass by billions of years of gravitational stirring, most notably by Jupiter. What remains is a small fraction of what once existed there, arranged into a pattern that, while not static, is far more stable than the early solar system's chaotic abundance. Without Jupiter's resonances to drive material out of the belt on the timescales they do, the distribution of asteroid orbits might be different, perhaps denser in certain zones, perhaps delivering a different pattern of close approaches and impacts to the inner planets over geological time. The belt we observe is not the belt that would exist in a solar system without Jupiter. It is a shaped thing, a curated thing, the product of billions of years of gravitational editing. Jupiter's gravitational rhythm is so consistent and so pervasive across the solar system that some scientists have described it as the metronome of the solar system, setting the tempo around which all other orbital motions organize themselves. A metronome keeps time without needing to be watched, without requiring acknowledgement from the musicians who depend on it. It simply ticks, steady and reliable, and everything that makes music in its presence adjusts to its rhythm. Jupiter's gravity operates in something like this way. It does not choose which objects to influence, does not distinguish between the dangerous and the harmless. It simply applies its gravitational rhythm to everything within its reach, and the solar system organizes itself around that rhythm over millions and billions of years. The order we observe in the solar system today, the relatively stable orbits, the cleared belt, the pattern of the Trojans, is, in significant part, a product of this patient, unwavering tick. Many scientists believe that Jupiter's regulatory role in the solar system was essential for the emergence and persistence of complex life on Earth. This is a hypothesis that sits at the intersection of astronomy and biology, two fields that rarely overlap but, in questions of habitability, find themselves in deep conversation. The argument is not that Jupiter planned any of this, not that it chose to protect the small blue world 5 orbits inward. It is simpler and stranger than intention. Jupiter's gravitational presence created conditions, a particular impact frequency, a particular orbital stability, a particular distribution of water-bearing asteroids that were compatible with the slow, fragile process of biological evolution. Change Jupiter's position, its mass, the timing of its formation, and the history of life on Earth changes with it in ways we cannot fully predict but can begin to model. Life, it turns out, is sensitive to the arrangement of the solar system it finds itself in. The rare Earth hypothesis, proposed by paleontologist Peter Ward and astronomer Joe Kirschvink, suggests that the specific conditions required for complex life, including a Jupiter-like gravitational regulator, may be uncommon in the galaxy. The hypothesis argues that what happened on Earth was not inevitable, not the natural and easy outcome of any planet with liquid water and a moderate climate. It was, instead, the product of an improbable accumulation of specific conditions: the right distance from the right star, a large moon to stabilize the axial tilt, a molten iron core generating a magnetic field, a protective outer atmosphere, and a giant planet in the right place with the right mass, playing the gravitational role that Jupiter plays. Not every star system has a Jupiter. Not every Jupiter equivalent sits where ours does. The combination, the specific arrangement that Earth inhabits, may be genuinely rare in a galaxy of hundreds of billions of stars. Jupiter's role in regulating the impact environment on Earth has reduced the frequency of the most devastating extinction-level events, allowing life longer periods of stability in which to evolve and diversify. Evolution is, above all else, a process that requires time. Time for mutations to accumulate, time for species to diversify, time for ecosystems to become complex. Mass extinctions reset parts of that process. They clear the board, eliminate what was built, and force evolution to begin new experiments from reduced populations. Jupiter has not prevented mass extinctions on Earth. The geologic record makes clear that they have occurred. But the spacing between major extinction events, the periods of relative calm in which life grew complex and diverse, may in part reflect the gravitational regulatory influence of Jupiter, keeping the largest and most frequent catastrophic impactors at bay and giving evolution the uninterrupted time it needed. Earth's relatively calm impact history over the last 500 million years, the period that encompasses almost all of complex animal life, is partly credited to Jupiter's ongoing gravitational influence on the surrounding debris field. 500 million years is the blink of an eye in cosmic time, but it is all of animal life. Every fish, every amphibian, every dinosaur, every mammal, every human civilization. In that time, Earth has been struck by large objects, but not nearly as often or as catastrophically as the Moon's battered surface might suggest is the norm. Part of the difference is Earth's active geology, which erases impact craters over time. But part of it is the actual impact rate, the frequency of significant collisions, which is shaped by the arrangement of the solar system and the presence of Jupiter's gravitational field, quietly sorting and redirecting the debris that might otherwise arrive here far more often. The Late Heavy Bombardment, a period roughly 4 billion years ago when Earth and the other inner planets were struck by an extraordinary number of large impactors, eventually ended, and Jupiter's gravitational settling was among the factors that contributed to that transition to a calmer impact environment. The Late Heavy Bombardment was, by any measure, a violent time. The Moon's oldest craters, the giant basins, the wide dark plains, were formed in this period, as were deep impact structures on Earth that have long since been erased by geology. What caused it and what ended it is still actively studied. One leading hypothesis involves the orbital migration of the giant planets, particularly Jupiter and Saturn, which disrupted the outer solar system and sent a surge of material inward. As those migrations settled and the outer solar system reached its current configuration, the bombardment faded. The violence of early planetary youth quieted into the relative peace that allowed life to persist. After Jupiter's orbit stabilized in approximately its current position, the rate of large impacts on Earth dropped significantly from the extraordinary levels of the early solar system. A transition that coincided with the first evidence of life in Earth's geological record. Life on Earth appears in the fossil record as early as 3.5 billion years ago, and chemical evidence suggests it may go back even further, perhaps to 3.8 or even 4 billion years, close to the end of the Late Heavy Bombardment. This timing is not necessarily a coincidence. As Jupiter settled, as the solar system's giant planets reached their current configuration and the flood of early impactors subsided, conditions on Earth became stable enough for the fragile chemistry of early life to persist. The planet cooled, oceans formed and held. And in those first calm oceans, something extraordinary began. A slow accumulation of complexity that would, after billions of years, result in everything that has ever thought about Jupiter. Some researchers believe that Jupiter's gravitational influence in the early solar system helped redirect water-bearing asteroids and comets inward, potentially contributing to the delivery of water to early Earth. The origin of Earth's oceans is one of the most fascinating unsolved questions in planetary science. Earth formed in a region of the solar system that was too hot for water ice to condense. The water that makes up our oceans must, at least in part, have been delivered from elsewhere. Asteroids and comets from the outer asteroid belt and beyond carry significant quantities of water ice, and the chemical signature of Earth's water most closely resembles that of certain outer belt asteroids. Jupiter's gravitational influence during the early solar system, including its migration phase, would have scattered significant quantities of this material inward. If this hypothesis holds, and the evidence continues to build, then Jupiter did not merely protect Earth's oceans, it may have helped put them there. The water in Earth's oceans, the water in every cloud, every river, every cell of every living thing, may partly trace its origin to asteroids that Jupiter redirected inward during the early solar system's turbulent formation period. This is one of the most poetic and strange truths in planetary science, that the water you are made of may have come from the outer solar system, delivered to Earth by the same gravitational forces that we are now discussing as potential protectors. Jupiter, in this reading of history, is not simply a guardian. It is partly an architect, a force that shaped the young solar system in ways that were not always gentle, not always beneficial in any simple sense, but that contributed to the specific chemical endowment that Earth received. The oceans, the rain, the water that flows in your veins, these are in part a legacy of the solar system's early turbulence, and Jupiter was at the center of that turbulence. Jupiter's role in the solar system's formation helped determine the final sizes and positions of the rocky inner planets, including Earth. In the standard model of solar system formation, the giant planets form first, from the abundance of gas and ice in the outer regions of the disk surrounding the young Sun. Once Jupiter formed and began migrating, moving inward and then outward through the disk of material, it sculpted the distribution of solid material available for the inner planets to accrete from. The size of Mars, which is far smaller than models would predict for a planet in its location, is thought to be a result of Jupiter's migration depleting the material in that region. Earth, by contrast, formed in a zone that retained enough material after Jupiter's influence was factored in to grow to its current size. The Earth we live on, its mass, its gravity, its geological activity, the very size of its molten core, is partly a product of Jupiter's formative influence. Jupiter's magnetic field is a phenomenon of extraordinary scale and power. The largest planetary magnetosphere in the solar system, a wonder of physics that generates awe in the scientists who study it. It is important to be clear about what Jupiter's magnetosphere does and does not do for Earth. It does not protect our planet from solar wind or radiation in any direct, meaningful sense. Earth is roughly 600 million kilometers from Jupiter on average, and our own planet's magnetic field and atmosphere handle the vast majority of that work themselves. But Jupiter's magnetosphere is worth understanding on its own terms, as a testament to the scale at which magnetic fields can operate, and as a reminder that the solar system contains phenomena that dwarf anything in our immediate experience. A magnetosphere that would span a visible arc larger than the full moon if our eyes could see it. That is not a small thing, even if its protection stops at Jupiter's own moons. Jupiter's magnetosphere is generated by the motion of metallic hydrogen deep within the planet's interior, a form of hydrogen that, under the crushing pressures far below Jupiter's visible cloud tops, conducts electricity like a metal and creates a powerful natural dynamo. This is one of the stranger facts in planetary science, that hydrogen, the simplest element, the first to form after the Big Bang, can be compressed to such densities that it loses its familiar properties and becomes something that behaves like liquid metal. At the pressures found deep inside Jupiter, millions of times the atmospheric pressure at Earth's surface, hydrogen atoms are pressed so tightly together that their electrons move freely, carrying electrical current. As Jupiter rotates, this vast conducting layer spins within it, generating a magnetic field of enormous intensity. It is a natural generator on a planetary scale, physics made visible through the behavior of the simplest element. The stability that Jupiter's gravitational presence has provided may have given Earth the 4 billion plus years it needed for intelligent life to emerge from the first simple chemistry. 4 billion years is not a number that means anything in a human lifetime, but it is the time it took for single-celled organisms to become multicellular, for multicellular life to become complex, for complex life to develop nervous systems, and then brains, and then eventually curiosity. All of that required an unbroken thread of time in which the conditions for life were maintained, in which the planet was not reset by catastrophic impacts too frequently, in which the slow accumulation of complexity could continue generation by generation. Jupiter's gravitational regulation of the solar system is one of the factors that helped maintain that thread. Not the only factor, not even necessarily the most important one, but a real one, woven into the fabric of the improbable story that resulted in every mind that has ever wondered about the stars. Jupiter's magnetic field is approximately 20,000 times stronger than Earth's magnetic field, one of the most powerful planetary magnetic fields in the solar system, second only to fields found around certain neutron stars. Earth's magnetic field is essential to our survival here. It deflects solar wind, shapes the Van Allen radiation belts, and has maintained the conditions for life across billions of years. Jupiter's field, 20,000 times more intense, operates on a scale that makes Earth's magnetic bubble seem modest by comparison. It shapes the environment around Jupiter and its moons in profound ways, trapping charged particles, generating intense radiation belts, driving spectacular auroras that dwarf anything visible on Earth. Understanding Jupiter's magnetic field is partly a lesson in how magnetic fields work at planetary scale, and partly an encounter with something so extreme it barely fits within familiar categories. Jupiter's magnetosphere is so large that if it were visible to the naked eye from Earth, it would appear larger than the full moon in the night sky, a vast, invisible bubble of magnetic field and trapped charged particles extending tens of millions of kilometers in all directions from the planet. The full moon, seen from Earth, spans about half a degree of arc across the sky, a modest but visible disk, the most familiar sight in the night sky after the Sun. Jupiter's magnetosphere, if it glowed visibly, would cover a region of sky multiple times larger, an immense ghostly structure extending outward toward the Sun and stretching an enormous tail away from it on the opposite side. We cannot see it, but it is there, always. A magnetic architecture of extraordinary size operating in the space between planets, shaping the environment through which everything in the solar system moves. Jupiter's magnetosphere traps vast quantities of high-energy charged particles from the Sun and from cosmic rays, creating radiation belts of extraordinary intensity around the planet itself. These radiation belts are among the most hostile environments in the solar system, far more intense than Earth's Van Allen belts, lethal to unshielded electronics and biological tissue in very short periods. The Galileo spacecraft, which orbited Jupiter for 8 years, had its instruments hardened against radiation but still accumulated significant damage over the course of its mission. For the moons that orbit within this radiation environment, particularly Europa and Io, the effects are dramatic. The surface of Europa is continually bombarded by high-energy particles that drive chemical reactions on its icy shell. Jupiter's radiation belts are a testament to the intensity of its magnetic field, and a reminder that power on this scale is indifferent to whether it is helpful or harmful. Jupiter generates its enormous magnetic field through a deep internal layer of metallic hydrogen, a state of matter that forms under pressures millions of times greater than the atmosphere we breathe. Metallic hydrogen was theorized by physicists long before it was confirmed, and Jupiter remains the most accessible natural laboratory for studying it. At the pressures found roughly 10,000 to 15,000 kilometers below Jupiter's cloud tops, ordinary molecular hydrogen, the gas that fills balloons that makes up most of Jupiter's visible atmosphere, transitions into a substance where electrons are no longer bound to individual protons. They flow freely, as they do in metals like copper or iron. And as Jupiter rotates rapidly, once every 10 hours, this vast conducting layer spins, generating the dynamo that powers the planet's magnetic field. It is an object lesson in how extreme conditions produce extreme phenomena, and how the interior of a gas giant is nothing like what the peaceful-looking clouds at its surface suggest. The metallic hydrogen layer in Jupiter's interior conducts electricity like a liquid metal, creating a natural planetary dynamo, the mechanism by which the rotation of conducting material in a magnetic field generates and sustains a magnetic field of extraordinary power. The dynamo mechanism is the same one that operates in Earth's molten iron outer core, generating our planet's comparatively modest magnetic field. In Jupiter, the conducting layer is hydrogen, a lighter element, a more exotic state, but the same fundamental physics. Electrical currents flowing through the rotating metallic hydrogen create loops of magnetic field. The rapid rotation of the planet, 10 hours for a full day on Jupiter compared to 24 on Earth, amplifies the effect, driving the currents faster and generating a field of proportionally greater strength. It is the same principle as an electric generator scaled up to the size of a planet, powered by nothing more exotic than rotation and physics. Jupiter's magnetosphere extends roughly 7 million kilometers toward the Sun on the sunward side and stretches into an enormous magnetotail that extends hundreds of millions of kilometers in the opposite direction, one of the largest structures in the solar system. The asymmetry is caused by the solar wind, the constant stream of charged particles flowing outward from the Sun at hundreds of kilometers per second. On the sunward side, the solar wind compresses Jupiter's magnetosphere, pushing it inward, limiting its extent. On the downwind side, the magnetosphere stretches outward into a long, sweeping tail, blown backward by the pressure of the solar wind like the tail of a comet. This magnetotail is enormous, so large that it can, at certain alignments, actually touch Saturn's orbit. Jupiter's magnetic reach is not merely planetary, it is, in a very real sense, interplanetary, a magnetic structure that spans a significant fraction of the inner solar system. Energetic particle bursts from solar flares, intense radiation-rich events on the Sun's surface, interact with Jupiter's magnetic field as they propagate outward through the solar system, though Earth's own magnetic field and atmosphere remain our primary protection against these events. This point deserves care. Jupiter's magnetosphere is not a radiation umbrella for Earth. The planet is too far away, the solar system too vast, and Earth's own defenses too robust for Jupiter to play a meaningful protective role against solar radiation at our location. But the interaction between solar energetic particles and Jupiter's field is real and scientifically important. It shapes the behavior of particles in the outer solar system, affecting the environments of Jupiter's moons and the readings of spacecraft in that region. Jupiter's field is a significant force in its local neighborhood. It simply does not extend its influence as far as Earth's orbit in any protective way. Jupiter's radiation belts are among the most intense in the solar system, regions of trapped high-energy electrons and protons that circle the planet in powerful rings generated and maintained by the interaction between the planet's magnetic field and the solar wind. The inner radiation belt, closest to the planet, is particularly intense. Electrons there have been measured at energies far higher than anything found in Earth's Van Allen belts. These are particles accelerated to tremendous energies by Jupiter's magnetic field, trapped in looping paths around the planet, their energy maintained by the dynamics of the magnetosphere. For spacecraft engineers, these belts represent a significant design challenge. Any probe that must fly through or operate within them requires extensive radiation hardening. For scientists, they represent one of the most energetic and exotic environments in the solar system, a natural laboratory for studying the physics of magnetic trapping and particle acceleration at extreme scales. While Jupiter's radiation belts are extraordinarily dangerous for spacecraft and would be lethal to unprotected living things, they represent enormous quantities of energy being held in a stable configuration around Jupiter, energy that, in a different solar system architecture, might propagate more freely through interplanetary space. This is not to say that Jupiter's radiation belts protect Earth. They do not in any direct sense. But the scale of energy contained within them is a measure of Jupiter's magnetic power, and that power is one of the most extraordinary phenomena in our cosmic neighborhood. A magnetic field strong enough to trap and maintain the energy of radiation belts more intense than anything in Earth's environment. That is a measure of what Jupiter is, of the scale at which it operates. It is not a protector in this context. It is simply vast, and vastness in the physics of magnetic fields creates containment as a natural consequence. The sheer scale of Jupiter's magnetic architecture, its magnetosphere, its radiation belts, its magnetotail, is a reminder that the solar system contains structures and phenomena that dwarf our most familiar experiences, operating through the same physics that governs a compass needle or the northern lights, simply at an almost incomprehensible scale. Physics does not change with size. The equations that describe the magnetic field around a refrigerator magnet describe, with the same mathematics, the magnetosphere that extends tens of millions of kilometers around Jupiter. The difference is only scale, and scale in the universe makes a profound difference to what a phenomenon looks like, how it behaves, and what effects it has on everything around it. Jupiter's magnetic architecture is one of the solar system's grandest expressions of this principle. Familiar physics, familiar forces, operating at a scale that turns them into something that requires entirely new words to describe. Jupiter's gravity is responsible for why the asteroid belt never coalesced into a full planet. Its persistent gravitational stirring prevented the material in that region from accumulating and growing into a single body. In the standard model of planetary formation, solid material in a disk around a young star gradually collects together. Dust becomes pebbles, pebbles become rocks, rocks become planetesimals, and planetesimals eventually merge into planets. This process worked in most regions of the early solar system. In the asteroid belt, it did not. Jupiter's gravity prevented the final stages from occurring. Its gravitational influence kept the relative velocities of objects in the belt too high for collisions to result in accretion rather than fragmentation. Objects that collided broke apart instead of merging. The material could not settle into a single world. The belt remained a collection of fragments, smaller, more numerous, and far less dangerous than a coherent planet would have been. Without Jupiter's gravitational interference, the material in the asteroid belt might have eventually formed a small rocky planet, but not a large one. The total mass currently in the asteroid belt is less than 4% of Earth's moon, far too little to build a Mars-sized world. Jupiter's role was not merely to prevent final assembly, it actively depleted the belt of most of its original mass over time. In the early solar system, the belt contained considerably more material than it does today. Jupiter's gravitational stirring drove much of it onto eccentric orbits, which led to energetic collisions that shattered and eventually removed material from the region, delivering some to the inner planets, ejecting some to the outer solar system, and sending some to be absorbed by the Sun. What remains is the residue of that depletion, a sparse, depleted belt that is a fraction of its original self, shaped and diminished by billions of years of Jupiter's gravitational influence. A fully formed planet in the region of the asteroid belt, even a small one, would have significantly altered the gravitational dynamics of the inner solar system in ways that would have been deeply disruptive to Earth's orbital stability. The inner solar system is a finely balanced gravitational arrangement, 4 rocky planets in stable, nearly circular orbits, their mutual gravitational influences keeping each other in predictable paths across geological time. Introduce a new planet into the asteroid belt region and that balance changes. The gravitational interactions multiply. Orbits that were stable may become unstable over millions of years. Earth's orbit, Earth's climate, Earth's seasons, all of these would be different in a solar system that had allowed a planet to form between Mars and Jupiter. Jupiter's disruption of that assembly process was, in this sense, not merely a prevention but a preservation. The inner solar system's delicate balance was maintained in part because Jupiter would not allow it to be disturbed. Jupiter kept the material in the early asteroid belt in a state of constant turbulence, preventing the large-scale accumulation of mass that would have been necessary for a planet to form. Turbulence is the enemy of accretion. For material to merge into a planet, collisions must be gentle enough, slow enough, low energy enough, for the pieces to stick rather than shatter. Jupiter's gravity kept the objects in the belt moving at speeds and angles that made gentle collisions rare. The kinetic energy of the belt's population was too high, the orbital velocities too disparate for any region of the belt to accumulate peacefully into a growing world. Instead of building, the belt broke. Collisions shattered rather than merged, and the debris of those shattered objects became the next generation of smaller, more numerous fragments. Jupiter's gravity maintained this turbulence for the entire history of the solar system, a sustained disruption that prevented order from asserting itself in the one place it was not wanted. The total mass of today's asteroid belt is less than 4% of Earth's moon, a surprisingly small amount for a region that contains hundreds of thousands of individually catalogued objects. This is one of the more startling facts in planetary science because the asteroid belt's visual representation, dense, crowded, dangerous, as portrayed in countless science fiction films, bears almost no resemblance to reality. The belt is mostly empty space. If you were somehow placed within it, the nearest asteroid would likely be hundreds of thousands of kilometers away. The total mass is tiny because Jupiter's gravitational influence depleted it so thoroughly over billions of years. Most of the original material is gone, scattered to the inner planets, ejected to the outer solar system, or absorbed by the Sun. What remains is a thin, sparse remnant of something that was once far more substantial, reshaped by the most dominant gravitational force in the solar system after the Sun itself. Jupiter's early migration through the solar system, a period when the young planet moved significantly closer to the Sun before being pulled outward again, redistributed vast quantities of rocky debris into configurations that shaped the final architecture of the inner solar system. The concept of a migrating Jupiter is one of the most dramatic and consequential ideas in modern planetary science. In the early solar system, gas giants were not fixed in their orbits. They moved, driven by interactions with the disk of gas and dust from which they formed. Jupiter moved inward, then was redirected outward by Saturn's gravitational influence, carving a path through the material of the inner disk that depleted and rearranged what was available for the terrestrial planets to form from. The migration happened over millions of years in the early history of the solar system, long before any life existed anywhere. But the effects of that migration are still visible today in the sizes of the inner planets, the mass of the asteroid belt, and the orbital arrangement of everything inside Jupiter's orbit. During Jupiter's early inward migration phase, its gravitational influence may have cleared material from the inner solar system that would otherwise have contributed to a more crowded, chaotic arrangement of small planets in the innermost region near the Sun. Some models of solar system formation suggest that without Jupiter's migration sweeping through the inner disk, the region between the Sun and Venus might have accumulated several additional small planets, a more densely populated inner system similar to what has been observed around some other stars. Jupiter's migration through that region is thought to have prevented this accumulation, depleting the material available for planet formation in the innermost zone. The relatively sparse inner solar system we have, 4 planets with significant gaps between them rather than a crowded swarm of small worlds, may be in part a legacy of Jupiter's early migration through material it then carried outward or disrupted on its journey inward. Jupiter's subsequent outward migration, driven by its gravitational interaction with Saturn, which formed slightly later and pulled Jupiter back toward its current position, helped settle the solar system into the relatively stable orbital architecture we see today. This outward migration is the second half of the Grand Tack scenario, a model that describes Jupiter's 2-phase movement through the early solar system. First inward, then outward, a gravitational dance with Saturn that gave the inner solar system its final settled form. As Jupiter moved outward, it stopped sweeping material from the inner disk and instead allowed the remaining material to begin the slower, more ordered process of planetary formation. The 4 rocky planets, Mercury, Venus, Earth, and Mars, formed in the wake of Jupiter's retreat, assembling from the depleted but now calmer material that remained. Jupiter's outward migration was, in this reading of history, the moment the solar system became recognizable as the one we live in. The Grand Tack hypothesis, named for a sailing maneuver in which a boat reverses direction, describes Jupiter's 2-phase migration as one of the most formative events in the history of our solar system's architecture. The name is apt. Like a sailing vessel tacking into the wind, Jupiter moved inward against the drift of the solar disk, then reversed as Saturn's gravity redirected it outward. This 2-phase movement, if the hypothesis is correct, explains several puzzling features of our solar system. The small size of Mars, the depleted asteroid belt, the relatively sparse inner solar system, and the specific orbital relationships between the giant planets. Not all planetary scientists accept the Grand Tack model fully. It is a hypothesis, not a settled fact, and the evidence that would confirm or refute it is difficult to obtain. But it represents one of the most compelling stories currently told about how the solar system became what it is today, and Jupiter is its protagonist. The Grand TAC model suggests that Jupiter's movements in the early solar system directly sculpted the size, mass, and position of Earth itself, that the planet we live on is, in a very real sense, a product of Jupiter's formative gravitational influence. This is perhaps the deepest way in which Jupiter's relationship with Earth is not simply protective, but generative. If the Grand TAC model is correct, the Earth you know, with its particular mass, its particular composition, its particular orbit, would not exist in the same form in a solar system where Jupiter had not migrated as it did. The depletion of the inner disk by Jupiter's passage and the subsequent settling of material as Jupiter retreated set the initial conditions for Earth's formation. Jupiter is, in this sense, not merely a guardian of Earth's existence. It is, in part, a reason for the specific form that existence takes, the particular size and orbit and composition of the world that holds the only life we know of in the universe. Over the last 600 million years, Earth has experienced fewer preserved large impact craters than the Moon, though the comparison requires care, because Earth is actually struck more often than the Moon, being a larger target with stronger gravity. The difference lies in preservation, Earth's active geology, plate tectonics, erosion, volcanic resurfacing, erases impact craters over time, while the Moon preserves every impact it has ever experienced in perfect, timeless detail. The Moon's cratered surface is not a record of what Earth has been spared. It is a record of what the Moon has accumulated in the absence of the geological processes that erase Earth's history. To understand how frequently Earth has been struck, scientists must look not at the number of visible craters, but at other evidence: shocked quartz, iridium layers in the geological record, and the slowly improving catalogue of Earth's ancient impact structures buried beneath continents and ocean floors. The Moon's cratered surface serves as an ancient record of the impact history of the inner solar system, a geological archive of collisions that occurred over billions of years, preserved in detail because the Moon lacks the atmosphere, water, and plate tectonics that erase Earth's own impact history. Every crater on the Moon tells a story. The vast, dark plains called Maria were formed by enormous impacts that melted the crust and flooded it with lava. The older, heavily cratered highlands record the violence of the late heavy bombardment. Younger craters, sharper and brighter with fresh ejecta, mark more recent events. When scientists want to understand the history of impacts in the inner solar system, their frequency, their size distribution, their timing, they read the Moon's surface the way a geologist reads rock layers, using age-dating techniques to assign dates to the craters and reconstruct the timeline of solar system violence. The Moon is, in this sense, Earth's geological diary, preserved in stone. Mass extinction events on Earth have occurred throughout geological history, but their frequency and spacing may reflect, in part, the gravitational regulatory influence of Jupiter on the distribution of large impactors in the inner solar system. The geological record of Earth contains evidence of at least 5 major mass extinctions, events that eliminated a significant fraction of all species on Earth in geologically brief periods. These events have multiple causes: volcanic eruptions, climate shifts, sea level changes, and in at least one case, the end Cretaceous extinction 66 million years ago, a large asteroid impact. The spacing of these events across geological time, the periods of relative calm between them, is one of the more challenging puzzles in evolutionary biology. Jupiter's role in regulating the impact environment is one of the factors that scientists consider when modeling extinction frequency. A distal but real influence on the most catastrophic events in the history of life. The Cretaceous-Paleogene extinction event, the impact that ended the age of non-avian dinosaurs 66 million years ago, was a rare event, not the norm. Major impact-driven extinctions of that scale are uncommon in Earth's geological history, and Jupiter's long-term regulation of the impact environment is one reason why such events do not occur more frequently. The Chicxulub impactor, the asteroid or comet that struck what is now Mexico's Yucatan Peninsula and triggered the extinction of 3/4 of all species on Earth, was an object roughly 10 to 15 kilometers in diameter. Events of that scale are extraordinarily rare. The geological record of the last 600 million years suggests that impacts capable of triggering mass extinctions occur on timescales of tens to hundreds of millions of years. The spaces between them, the long periods of relative calm, are the intervals in which complex life diversified and flourished. Those spaces in part reflect the gravitational order that Jupiter imposes on the solar system. Jupiter's influence over billions of years has contributed to giving Earth an impact history that, while not gentle, has been regulated in ways that allowed the long unbroken thread of biological complexity to persist. Life on Earth has survived. That is, in the broadest view, the most important fact in all of biology, that despite 4 billion years of geological violence, asteroid impacts, volcanic eruptions, ice ages, and mass extinctions, the thread of life has never fully broken. Every species alive today is the descendant of survivors, of lineages that found their way through each catastrophe and persisted into the next period of calm. The frequency of catastrophes, the depth of the resets, the length of the recovery periods, all of these are shaped by the environment the solar system provides. Jupiter is one of the forces that shaped that environment over timescales that dwarf the entire history of multicellular life on Earth. Paleontologists note that life rebounded after each mass extinction in Earth's history, in part because the extinctions, however devastating, were spaced far enough apart to allow complex ecosystems to rebuild before the next catastrophic event. Recovery from a mass extinction is slow. After the end Cretaceous event, it took roughly 10 million years for ecosystems to recover their former complexity, for forests to return, for marine ecosystems to rebuild their food webs, for the diversity of species to approach pre-extinction levels. If mass extinctions occurred more frequently, if the spacing between them were compressed, recovery might never be complete before the next reset. The fact that Earth has experienced major extinction events tens of millions of years apart rather than millions of years apart is significant for the evolution of complexity. Jupiter is one of the factors that contributes to that spacing, by regulating the frequency of the largest impactors rather than permitting a more constant reign of extinction-level events. Jupiter's long orbital period, 11.86 Earth years for a single orbit of the Sun, means that its gravitational sweeping effect cycles regularly through the solar system on a timescale that is short compared to geological time but long compared to a human lifetime. Every orbit of Jupiter is a complete cycle of its gravitational reach, a full rotation of the planet around the Sun during which its gravity has influenced every part of its orbital domain. On geological timescales, Jupiter has completed this orbit hundreds of millions of times, each orbit contributing incrementally to the sorting, clearing, and regulating of the solar system's debris field. The regularity is important. Jupiter's influence is not sporadic or random. It is rhythmic and continuous, a repeating pattern of gravitational interaction that, accumulated over deep time, has shaped the distribution of material in the solar system in ways that are still being mapped and understood. Over geological deep time, Jupiter's repeated orbital cycles have gradually contributed to clearing much of the inner solar system of the loose debris that was abundant in the earliest period of solar system history. The contrast between the early solar system and the one that exists today is dramatic. 4 billion years ago, the inner solar system was a far more crowded and violent place, dense with debris, rich with impactors, reshaped by collisions on timescales of thousands rather than millions of years. Today, that violence has subsided enormously. Most of the original debris has been swept away, absorbed by the Sun, incorporated into planets, or ejected from the solar system. Jupiter's gravitational influence is one of the primary reasons for that change, working over billions of years to sort and remove material that once made the inner solar system far less hospitable to anything that might be trying to live there. Earth's biodiversity today, every species of plant, animal, fungus, and microorganism, is the evolutionary inheritance of billions of years during which Jupiter's gravitational presence was one of the factors maintaining the conditions necessary for life to persist and diversify. This is the final, deepest sense in which Jupiter's role in Earth's story is meaningful, not as a shield, not as a filter, but as one of the background conditions that allowed the extraordinary experiment of biological complexity to run long enough to produce its most intricate results. Every species alive today is the product of continuous, unbroken lineages stretching back billions of years. Every one of those lineages survived through the periods between catastrophes, the long, quiet eons in which evolution could work, in which ecosystems could grow complex, in which the raw material of life could be elaborated into the extraordinary diversity we observe. Jupiter helped maintain the conditions for those quiet eons. And in those quiet eons, everything alive today came to be. The story of life on Earth cannot be told without reference to the solar system it lives within. And the solar system it lives within cannot be understood without reference to Jupiter's billions of years of gravitational influence on its architecture. Life and astronomy are usually treated as separate subjects, one about the small and intricate, the other about the vast and ancient. But in the question of how Earth came to be habitable, how life emerged and persisted, and why the solar system has the specific arrangement it does, the two subjects are inseparable. The carbon in living cells was forged in ancient stars. The water in Earth's oceans may have been delivered by asteroids redirected by Jupiter. The spacing of mass extinctions reflects the frequency of large impactors, which reflects Jupiter's gravitational regulation of the debris field. Biology, in its deepest roots, is a consequence of astronomy. And Jupiter is one of the central figures in the astronomical story that made biology possible. Exoplanet systems that lack a Jupiter equivalent in the outer region of the system show different inner planet orbital dynamics compared to systems where such a giant planet exists, suggesting that the presence or absence of a gas giant companion has measurable effects on the stability of inner planetary systems. The discovery of thousands of exoplanets in the last 3 decades has given planetary scientists an enormous comparative data set, a library of solar systems with different architectures, different compositions, different arrangements of planets. Among the patterns emerging from this data is a correlation between the presence of outer gas giants and the orbital stability of inner rocky planets. Systems without an outer giant tend to have inner planets with more eccentric orbits on average. The causal relationship is complex and debated, but the observational pattern is real, and it suggests that Jupiter's role in stabilizing Earth's orbit may not be unique to our solar system, but part of a broader principle about how planetary architectures affect habitability. Computer simulations that remove Jupiter from our solar system and model the resulting dynamics over millions of years show Earth's orbit becoming progressively more chaotic and irregular, potentially destabilizing the climate over geological timescales. These simulations are not predictions of imminent danger. Jupiter is not going anywhere, but they are illuminating experiments in planetary physics, allowing scientists to understand what Jupiter's presence contributes by seeing what the solar system looks like in its absence. The results are consistently sobering. Without Jupiter's gravitational anchor, the inner planets develop less stable orbital relationships over millions to hundreds of millions of years. Earth's orbit, currently nearly circular, may become more elliptical. Seasonal patterns may become more extreme. The consistency of the climate, which life depends on across geological timescales, may be compromised. Jupiter's presence is not neutral. Removing it changes the story of every planet that remains. Simulations of an Earth without Jupiter's gravitational regulation show a different impact history, though the direction of that difference is more nuanced than simply more impacts. Some models suggest that certain classes of impactors, particularly outer solar system comets that Jupiter currently redirects or captures, would behave differently in a Jupiter-free solar system. Some would remain in the outer solar system, never disturbed onto inner planet crossing trajectories. Others might arrive more frequently, no longer deflected by Jupiter's gravity. The net effect on Earth's impact rate is model-dependent and scientifically contested. What is not contested is that the impact environment would be different, substantially different in some models, modestly different in others. Jupiter is not a perfect shield, and removing it does not simply open a floodgate. It reshapes the gravitational landscape of the entire solar system, and the consequences ripple through every aspect of what the inner planets experience. Some exoplanet systems have hot Jupiters, gas giants that migrated all the way to very close orbits around their host stars, and these systems tend to lack stable inner rocky planets, suggesting that a Jupiter analog must be in the right place to be beneficial rather than destructive. A hot Jupiter is, in a sense, a cautionary tale about what happens when a gas giant migrates too far inward. As it sweeps through the inner disk during its inward journey, it disrupts the formation of rocky planets in the habitable zone, clearing the material those planets would need to form or ejecting them entirely. Our Jupiter stopped its inward migration and reversed, a piece of fortunate orbital choreography that allowed the inner solar system to form and persist in its current configuration. Hot Jupiter systems, by contrast, are dominated by their gas giant in the most direct way. The giant came too close, swept too much, and left nothing habitable in the inner system. The position matters as much as the presence. Our Jupiter's orbital distance from the Sun, averaging about 5.2 astronomical units, appears to sit in a range that allows it to regulate the inner solar system without disrupting it. This is not a guaranteed feature of all solar systems. Gas giants can form at a variety of distances from their stars, and their migration patterns can move them significantly from their formation locations. A Jupiter at half its current distance would interact with the asteroid belt and the inner planets very differently. Its gravitational resonances would fall in different places. Its tidal effects on the inner planets would be stronger. Its influence on the orbital dynamics of Venus and Earth would be more pronounced. A Jupiter at twice its current distance would be more distant, less influential, potentially leaving the inner solar system with less gravitational regulation. The distance Jupiter occupies is, like so many features of our solar system, part of the specific arrangement that makes Earth's history possible. Astronomers studying exoplanet systems now factor in the presence or absence of Jupiter-like outer planets as one of the criteria relevant to assessing the potential habitability of inner rocky planets in those systems. The search for potentially habitable worlds has grown more sophisticated since the first exoplanet discoveries in the 1990s. Early efforts focused primarily on finding Earth-sized planets in the habitable zone, the range of distances from a star where liquid water could exist on a planet's surface. More recent work incorporates the broader context of the planetary system, the presence of a large moon, the star's variability, the system's metallicity, and the existence of a Jupiter-like outer planet. A rocky planet in the habitable zone of a star with no outer giant companion is considered by some researchers to be in a different habitability category than one with a gas giant guardian. The assessment is nuanced and contested, but the consideration is real. The search for Earth-like exoplanets increasingly incorporates factors beyond planetary size and temperature, including whether the architecture of the surrounding planetary system includes the kind of gravitational regulation that Jupiter provides in our own solar system. This represents a significant evolution in how scientists think about habitability. A planet is not a closed system. It exists within a solar system, and the properties of that solar system shape its long-term evolution in profound ways. A rocky planet around a Sun-like star in the habitable zone with liquid water and an atmosphere may still have a very different long-term history depending on what companions share its solar system. The presence of gas giants, their masses and orbital positions, the stability of the overall system architecture. These are increasingly recognized as relevant factors in assessing whether a given exoplanet is the kind of place where complex life might have the time and stability to emerge. NASA's planet hunting missions and the research programs they support now include planetary system architecture, including the presence of outer giant planets, as part of the framework for evaluating the astrobiological potential of newly discovered planetary systems. The James Webb Space Telescope, launched in 2021, is capable of studying the atmospheres of exoplanets in far greater detail than any previous instrument. But the context for interpreting what it finds, whether a detected atmosphere is compatible with complex life, requires understanding the system as a whole. A planet with biosignature gases in its atmosphere, orbiting in a habitable zone, is a more compelling candidate if its solar system includes a stabilizing outer giant than if it exists in a dynamically chaotic system prone to orbital instability and frequent large impacts. The lessons learned from studying Jupiter's role in our own solar system are being applied directly to the evaluation of every new planetary system that future missions discover. Our solar system's architecture, with Jupiter at 5.2 astronomical units, Saturn further out, and 4 rocky inner planets in relatively stable, nearly circular orbits, may be rarer than scientists once assumed. Early models of planetary formation suggested that solar systems like ours would be common around Sun-like stars. The first exoplanet discoveries shattered that assumption. The universe turned out to be rich with planetary systems, but few of them look much like ours. Hot Jupiters, super-Earths in tight orbits, systems with no analogue to our outer giants, systems with gas giants in eccentric orbits that would destabilize any inner rocky planets. The variety is enormous, and our solar system's architecture is not the dominant type. This does not mean we are unique, but it does suggest that the specific combination of features that makes Earth's history possible, including Jupiter in its current position, may represent one end of a distribution, the particular arrangement that happened to produce, among other things, us. As recently as 2016, amateur astronomers recorded a fresh impact flash on Jupiter. A brief, brilliant point of light against the planet's cloud bands that lasted only seconds before vanishing, evidence of a small body striking the planet's upper atmosphere at tens of kilometers per second. The 2016 event was observed independently by multiple amateur astronomers in different countries, a remarkable testament to the global community of skywatchers who monitor Jupiter regularly and in detail. These are not professional scientists, necessarily. They are people who spend clear nights at their telescopes because they love what they see there, because Jupiter's belts and storms and moons provide an endlessly changing view of a world unlike anything on Earth. And in the course of that patient watching, they catch moments that professional observatories with their automated survey programs sometimes miss, the flash and fade of a small world ending its journey in Jupiter's endless atmosphere. In 2019, another impact flash was recorded on Jupiter, one of several observed in recent years by the growing community of amateur and professional astronomers who monitor the planet's disk for exactly these transient events. Each observed impact is, in a sense, a data point, a confirmation that Jupiter continues to actively intercept and absorb material from the solar system's debris field in real time, in the present era, not just in the ancient past. The frequency of these observed events, corrected for the fraction of Jupiter's disk that is actually being monitored at any given moment, suggests that small impacts occur far more often than the handful that happen to be caught on camera. For every impact that an amateur astronomer records, there are many more that happen when no telescope is pointed in the right direction, at the right moment, with the right equipment to capture the brief flare of light. Scientists estimate that Jupiter experiences dozens of small impacts each year. Events too small to leave visible scars in the atmosphere for more than a few hours, but large enough to release energy equivalent to significant nuclear detonations in the planet's upper cloud layers. These estimates come from statistical extrapolation, combining the observed impact rate with models of the size distribution of impactors and the fraction of Jupiter's disk that is under observation at any given time. The result is a picture of Jupiter as an actively bombarded world, not a static, unchanging sphere, but a dynamic object that continuously interacts with the debris field of the solar system, absorbing small objects with regularity and larger ones on the rarer timescales that follow the size distribution of impactors. Jupiter has always been doing this. It will continue doing it for as long as the solar system exists. The bombardment does not end, it simply continues quietly in the dark. Modern observatories and dedicated monitoring programs now watch Jupiter's disk specifically to track and record impact events in real time, turning the planet into a living laboratory for studying the frequency and size distribution of objects in the solar system's debris field. The DETECT project, a collaborative effort between amateur astronomers and professional scientists, coordinates impact monitoring across a global network of telescopes, analyzing footage of Jupiter's disk for the telltale bright flashes that indicate impacts. This citizen science approach has significantly increased the detection rate of impact events and provided a growing dataset that helps scientists calibrate their models of the solar system's impactor population. Every detected flash adds to the statistical picture of how often Jupiter intercepts material, and that picture in turn informs our understanding of the broader impact environment that Earth and the other inner planets exist within. Each observed impact on Jupiter provides scientists with information about the size, composition, and frequency of objects in the near-Jupiter region of the solar system, data that is directly relevant to understanding the broader impact environment that Earth exists within. The flash of light produced when an object strikes Jupiter's atmosphere encodes information about the event. Its duration and brightness indicate the size of the impactor and the energy of the collision. The location on Jupiter's disk, the time of year relative to Jupiter's position in its orbit, and the frequency of events in different observing periods all contribute to statistical models of the impactor population. These models are not purely academic. They inform planetary defense assessments, help scientists understand the size distribution of near-Earth objects, and provide ground truth for theoretical models of how debris is distributed in the inner and outer solar system. Jupiter's ongoing impacts are, in this sense, a continuous gift to planetary science. Jupiter's observed impact record helps calibrate the asteroid and comet threat models that planetary defense agencies use to assess the long-term risk of large impacts on Earth, making the study of Jupiter's bombardment history directly relevant to protecting our own planet. Planetary defense, the effort to identify, track, and if necessary, deflect objects that might pose a threat to Earth, depends fundamentally on understanding the population of potential impactors, their numbers, their size distribution, their orbital characteristics, and the rate at which they encounter Earth-crossing trajectories. Jupiter's impact record contributes to this understanding in two ways. Directly, by providing observed data on impact frequency in the outer inner solar system region, and indirectly, by helping scientists understand how Jupiter's gravity shapes the population of objects that might eventually cross Earth's orbit. Every Jupiter impact observed is a data point in the larger model of solar system hazards. NASA's planetary defense efforts factor in Jupiter's gravitational influence when building models of the long-term risk that asteroids and comets pose to Earth, acknowledging the planet's complex, nuanced role as both a redirector of some threats and an occasional source of others. The Planetary Defense Coordination Office, established by NASA in 2016, coordinates the detection, tracking, and characterization of near-Earth objects, asteroids and comets that come within about 1.3 astronomical units of the Sun, crossing or approaching Earth's orbit. The orbital models used to project the future trajectories of these objects over decades and centuries must account for the gravitational influences of all the major planets, including Jupiter. In some cases, Jupiter's gravity can redirect a tracked object away from Earth in future orbital cycles. In others, it can draw an object onto a more threatening trajectory. The full picture requires treating Jupiter not as a simple protector, but as a significant gravitational variable whose influence must be carefully modeled. The existence of planetary defense programs like NASA's Planetary Defense Coordination Office is, in part, a product of the scientific understanding that the solar system's debris field continues to interact with Earth, an understanding sharpened by decades of studying how Jupiter regulates that debris field and what the inner solar system experiences as a result. The recognition that Earth is not immune to large impacts, that the geological record contains evidence of past catastrophes, and that the population of potential impactors still exists, motivated the creation of systematic planetary defense programs. Studying Jupiter's impact history was one of the paths that led to this recognition. The Shoemaker-Levy 9 event in 1994, watched by the entire world, made viscerally real the possibility of catastrophic impacts in the modern solar system. Jupiter's visible vulnerability reminded humanity that the solar system is not a safe, static place, but a dynamic environment in which large collisions are not merely ancient history. Ancient astronomers named Jupiter after the king of the gods, and in doing so, without knowing any of the physics we have discussed tonight, they honored something real. They could not have known about orbital resonance, about the Kirkwood gaps, about the Grand Tack migration, about metallic hydrogen dynamos, or Lagrange points, or gravitational wells. They had only what they could see, a point of light, steadier than the stars, brighter than almost anything in the sky, moving with slow and majestic regularity through the constellations. Something in that regularity, that brightness, that unhurried motion across the sky must have communicated authority to them, a sense that this light was not like the others, that it occupied a different order of significance in the sky above their heads. They named it for their highest god, and they were, in ways they could not have articulated, right? Every ancient culture that observed the night sky with care, Babylonian astronomers, Greek philosophers, Chinese imperial star watchers, Maya calendar makers, noted Jupiter's brightness and its dominance among the wandering lights. Some cultures worshipped it as a protector deity. They were encoding in the language of myth and religion something that would take us millennia of mathematics to understand in its full depth. The sky watchers of Babylon tracked Jupiter with extraordinary precision, recording its positions over centuries and using them to predict its future appearances. The Greeks made it the throne of Zeus. The Romans made it the patron of their civilization. The Maya incorporated its synodic period into their complex calendrical systems. None of them knew what Jupiter was, a gas giant 11 times the diameter of Earth, 40 minutes light travel away. But they recognized its presence, and they gave that presence the weight it deserved. The Voyager missions, Voyager 1 and Voyager 2, launched in 1977, flew past Jupiter in 1979 and revealed for the first time a world of extraordinary complexity and beauty, a churning, banded atmosphere of amber and cream and russet threaded with storms of every scale, surrounded by a system of moons more geologically diverse than anything anticipated. Before Voyager, Jupiter was a disk in a telescope, beautiful and mysterious but unresolved, its surface patterns visible but its true nature unknown. After Voyager, it became a place, an actual world, complex and dynamic, alive with weather patterns that had been churning for centuries, accompanied by moons that turned out to have volcanoes and ice-covered oceans and ancient cratered plains. The images sent back by Voyager across hundreds of millions of miles of space changed not just what we knew about Jupiter, but how we understood the word world. How many kinds of world the solar system contained, how rich the universe was in places unlike our own. Jupiter's Great Red Spot, an anticyclonic storm larger than the entire Earth that has persisted for at least 350 years of recorded observation and possibly far longer, is a reminder of the raw, patient power of the world that stands between us and the outer solar system. The Great Red Spot is, in its way, a monument to Jupiter's scale, a storm that would swallow our entire planet, that has raged with sustained energy for longer than most of the nations on Earth have existed, that is driven by heat rising from Jupiter's interior and maintained by the dynamics of a rapidly rotating atmosphere. This is not a gentle phenomenon. It is a demonstration of energy and persistence on a scale that is difficult to comprehend. And yet, from Earth, it appears as a small reddish oval, a delicate feature on the surface of a distant world. The universe is very good at hiding its violence behind beauty, and Jupiter is one of its finest examples. In all its silent grandeur, its storms and moons, its magnetic tempests and gravitational authority, its billions of years of patient orbital work, Jupiter asks nothing. It has no awareness of what it does, no intention behind the impacts it absorbs or the orbits it sculpts or the water it may have helped deliver to a small blue world. It simply holds its place in the dark, year after year, orbit after orbit, completing its great circuit of the Sun with a regularity that has not wavered across all the time that life has existed on Earth. And in that holding, in that unwavering presence, something extraordinary has been possible. A small planet, in a quiet corner of one galaxy among hundreds of billions, with liquid water and a stable climate and enough uninterrupted time, has produced creatures who can look up at the night sky and recognize in a steady golden light the ancient companion that helped make their existence possible. And so we return to that steady light above the horizon, the one that has always been there, patient and unhurried, moving through the dark on its great slow circuit. Jupiter does not protect us perfectly. It does not shield us the way a wall shields, does not guard us the way a soldier guards. It simply exists, enormous and ancient, holding the gravitational order of the solar system the way a deep note holds a piece of music, as foundation, as steadiness, as the low hum beneath everything else. You are here, in part, because of that hum. Because billions of years of gravitational work shaped the solar system into a place calm enough for life to try, and patient enough for life to succeed. Let that settle into you now, as softly as starlight, as quietly as the turning of the world. You are held. You have always been held. Sleep well.